Hey everyone, my name is Nadav and I manage the machine learning group at Booking.com's Tel Aviv Machine Learning Center. Today, I will present a work that was done by my colleagues Pavel Levin and Benjamin Gutelman at our center. In this work, we'll see how we developed a gallery of representations for hotels using multitask learning. For those of you who are not familiar with Booking.com, we are the leading online travel marketplace. Established almost 25 years ago, Booking.com has around 17,000 employees around the globe. We have over 29 million property listings on our website. In our products, we have over 200 machine learning models deployed that serve millions of customers every day. We have a dedicated machine learning center here in Israel with around 50 people and growing. At Booking, we deal with a variety of ML problems like ranking properties, personalizing the user experience in the website, fraud detection, etc. To be able to make good and efficient predictions across all of our use cases, we need good representations for our data. Over the past 20 years or so, web experience has become much more visual and engaging. What you can see in this slide is the transformation that Booking's website has gone through the years. As you assume, most websites that have been around that long have become much more visual as well. It's been long established that understanding images can enable better personalization and more effective user experience in general. Specifically in e-commerce setting, we have products with photo galleries which contain lots of information. In this work, we outline a general framework that shows we can learn useful product representation from its image gallery using multitask learning. This representation is eventually a fixed size vector, an embedding. We'll demonstrate how we can use this embedding for downstream applications. In addition, we'll show the comparison between two approaches for multitask learning. To motivate why images are so interesting in our setting, consider images of a swimming pool. Swimming pool is quite an important facility for our business, as it plays a major role in the decision of booking an accommodation. When users view the images in this slide, for instance, they can learn a lot about the difference between the swimming pools. A binary representation that will describe whether the hotel has a swimming pool or not will obviously fail in capturing a lot of the information about the type of the swimming pool. For instance, take a look on the right image. Would you like to stay at that accommodation? I guess not. Representing the image details in a structured and usable format that will contain enough information to understand stuff like user decisions or other characteristics of the hotel is not a trivial task. When we are scaling up to image galleries, the problem becomes much more complex. In vision, you need to have a representation that will capture all the important information from the entire gallery for different use cases. The way we address this problem is by using other structured data we have about the property as supervision signals for training. So, how did we approach this problem? In this slide, you can see our end-to-end solution. It consists of image encoders incorporating VGG16 architecture. For each image in the gallery, we get an embedding, and eventually we aggregate all those embeddings using mean pooling. In addition, the parameters of the encoders are shared. This allows us to have a permutation invariance property, meaning the order of the input images is not affecting the final result. We then take the global embedding and use it to train independent tasks using simple shallow models. Finally, we aggregate the different losses into a multitask loss. The framework itself is quite general, and it's possible to replace different parts of it, like the encoders, the pooling mechanism, the specific task architecture, etc. Now, let's briefly discuss how we actually do the multitask learning and how we combine the different losses. So, in our problem, we try two variants of weighting the task-specific losses. The total loss is the aggregation of binary, categorical, and regression losses. The first weighting approach is a simple heuristic based on uniform scaling, in which the regression loss, which has a different scale, is normalized by the sample variance. In the second approach, we use Kendall's solution from CVPR 2018. In this approach, the losses are all normalized using learned scaling factors. So the main difference is that in the second approach, the factors are actually learned from the data. Let's get a little into the training details. First, on the right, you can see the different tasks used for training. It consists of categorical tasks like predicting the country of the property and also the city which has the highest cardinality. It also consists of binary tasks like understanding whether the property has a picnic area, access to the beach, a kitchen, balcony, etc. And lastly, regression tasks like the distance from city center in kilometers or the average length of stay in days. We trained the model on around 500,000 accommodations with a gallery size between 5 to 44 images. We used TensorFlow and a single GPU. In this slide, we can visually inspect the projected gallery embeddings after training. If we color code them according to specific business labels, we can see nice structure on different aspects like the property type, the region of the hotel, etc. One thing that is of big interest to us is to check how those embeddings perform when using downstream tasks. Here, we use a downstream task trying to predict the star rating of a property. We try to predict that using a shallow model that uses the embedding as input features. Note that we didn't use any form of this label in training. We compared our results against two baselines, embeddings taken from a pre-trained VGG16 on ImageNet, and the second one is our architecture trained end-to-end on the star rating task only. As you can see, using multitask learning embedding consistently outperforms the other baselines. We can get some explanation for this by observing the star rating visualizations from the previous slide, in which we could see some structure although it wasn't used in training. Lastly, we get an obvious computational gain if we use embedding in shallow models, both in inference and training. Another evaluation we performed is how well specific tasks do when trained as part of the multitask learning setting versus the optimal end-to-end training on a single task. As expected, most of the times the optimal single task training is doing better. The x-axis specifies what's the percentage of accuracy degradation when using multitask learning, meaning if we have negative percentage, we actually do better than the optimal setting. The orange and blue results are simply using different scaling approaches. We can see some binary and regression tasks in which the multitask learning approach actually did better than the optimal setting. This occurred in binary tasks like identifying whether the property has access to the beach or whether it has sea view. We can also see that we have a multi-class task like C1 trying to predict what city the property belongs to. In general, we can see that the blue pseudo-uniform scaling, on average, outperformed Kendall's approach in our setting. We were also interested to evaluate how binary tasks, which consist of the majority of tasks we have, do when we have high-class imbalance. On the x-axis, you can see the amount of imbalance. On the left are the most imbalanced tasks. On the y-axis, we can see the performance improvement when training multitask learning versus the optimal end-to-end model with a single task. If it's over 1, it means multitask learning did better. Observing the figure, we can see a strong statistical correlation, meaning the more imbalance we have, the more we benefit from using multitask learning setup. This is intuitive, as the more imbalance we have, the less signal we have on that task, meaning we can learn more from other tasks. Finally, we can see some application that uses our method. On the left image, you can see visual search that result in ranked list of properties. On the right image, you can see match properties based on their image galleries, what we're calling similar properties. That's it. Thanks a lot for listening, and thanks again to my colleagues Pavel and Benjamin for this very nice work. We're hiring to the Tel Aviv Machine Learning Center. Feel free to reach out for any questions you have. Bye.